Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss on the module Nanoscience and Nanotechnology, an introduction from the paper Nanoscience and Nanotechnology first. So students, after completing this module, you will be able to know the following. First, nanoscience and what is nanotechnology. Secondly, we will discuss about the nanomaterials along with their types. Third, we will also discuss about the length and the time scale. Lastly, we will discuss how do we build the nanostructured objects. So we'll discuss two methods in this. First is top-down approach and second is bottom-up approach. So students, let us start with a basic introduction about the module. Nanoscience and nanotechnology are being envisaged as the science and technology of the future. They are being expected to transform our understanding of almost every natural phenomenon. Nanotechnology is predicted to revolutionize every aspect of human life. However, the technology itself is in its nascent stage and needs comprehensive understanding of the various aspects of objects at which it is applicable. So this module provides the essential insights into the dimensions which are relevant to this technology. Nanoscience. Nanoscience is the study of processes and manipulation of materials at atomic or molecular scale such that the properties vary considerably than at the larger scales, that is, bulk materials. So, nanoscience can be classified into four categories. That is, in order to fabricate the nanostructures, nanostructured, nanotools, and finally, we can fabricate nano devices. Nanostructures can be of various types, that is, fullerenes, nanotubes, nanowires, nanofibers, nanoparticles, and quantum dots. Nanostructured consist of nanoscaled microstructures in bulk or thin films, nanograins, nanocrystalline materials, nanocomposites. Nanotools consist of fabrication techniques, analysis and metrology, software for nanotech. Lastly, we have the nano devices, that is electronic devices, NEMS devices, bio devices, lab on a chip, biosensors, drug delivery, data storage, catalysis, nanoscaled machines. Now, students, the question arises, why nano? At the nano scale, strange things happens to the materials. That is, their properties changes. So, what types of properties changes? Reactivity. As the particles get smaller, they tend to react differently with their environment than the larger particles. Next is the size. So smaller particles can have different optical properties. Their colors changes because different sizes of particles reflect and absorb the light differently. Next is magnetism. Now smaller particles can have different magnetic properties than the larger one. So according to this table, the magnetism in bulk and in nanoparticles are tabulated. That is the sodium. In bulk, it is paramagnetic, and when we prepare the nanoparticle, it becomes ferromagnetic. In the case of iron, cobalt, nickel, ferromagnetic in the bulk changes to super paramagnetic in the case of nanoparticles. Next, we have galadium and Tb, where the ferromagnetic nature in the bulk changes to super paramagnetic in nanoparticle. Next is ruthenium, whose paramagnetic nature in the bulk changes to ferromagnetic in the case of nanoparticle. Now, these are some of the examples which has been shown over here. That is, first is the reactivity. Now, as you can see, there are two types of or the two forms of sugar. First is the granulated sugar and the second one are the sugar cubes. So, as you can see over here, which one dissolves faster in water? Obviously, the answer is the granulated sugar. Next is about the size. Now, as you can see, there are different sizes of gold nanoparticles. So, gold demonstrates very different properties, that is optical, electrical, mechanical, etc. at nanoscale. So, differently sized particles reflects and absorbs light differently. What is nanotechnology? The development of materials and devices by exploiting the characteristics of particles on the nanoscale by humans. Now there are potential impacts of nanotechnology. First is health. In diagnostics, cancer treatment and targeted drug delivery. Second, in the case of materials, sports industry, cosmetics, clothing and space elevators. Next, in the case of technology, faster processing, morphing, computers and smaller and more powerful mobile devices. Lastly, in the case of environment, cleaner energy, better energy storage and water treatment. Let us now discuss about the nanoparticles. First, let us discuss its origin. So, they can be natural, they can be unintentionally released, and they can be manufactured. Now, they are dispersed in gases, that is, in the aerosols, liquids, gels, ferrofluids, solids, matrix materials. In the aggregation state, they can be single particles, they can aggregate, or they can agglomerate. So, nano capsules, they are of different form. Nanocapsules, quantum dots, nanoparticulate materials, nanotubes, ultra-fine aerosols. Their chemical composition varies or consists of metals, metal oxides, polymers, carbon, semiconductors, biomolecules. Their shape varying from spheres, needles, platelets, tubes, or wires. Now, nanoparticles, their surface can be modified when untreated, coated, or coated with some core or shell particles. Nanoparticles, their example. So, this is shown as the fullerene, whose the total diameter is 1 nanometer, that is, in which there are 60 carbon atoms linked together in one unit. Now, as you can see in the second figure, that is, in the 1 nanometer, there are 3.5 gold atoms. So, this is how the nanoparticles can be exampled, and here you can see that in the case of gold atoms, they are positioned adjacently in a row. Now students, next question arises is that how big is the nano? So we have the ratio of the earth to football is equal to the ratio of football to the fullerene. So now you can imagine that how big is your nano. So now, or we can classify the nanomaterials according to their dimension, that is, the objects with at least one dimension in the nanometer range, that is 1 to 100 nanometer, are termed as nanomaterials. So they have been tabulated over here. If we have all the three dimensions less than 100 nanometer, then we say it is a nanoparticle, a quantum dot, nanoshell, or a nanoring, etc. If we have two dimensions less than 100 nanometer, then we can say it to be nanotube, nanofibers, nanowire, etc. Next one is having one dimension less than 100 nanometer, then we say it to be a thin film, a layer, or a coating. Let us now discuss the types of nanomaterials. Nanomaterials are broadly classified into two types: non-intentionally produced nanomaterials. So these are the nano-sized particles or materials which are present in the environment naturally. For example, proteins, viruses, nanoparticles released from volcanic eruptions, etc., or as a result of human activities. For example, particles emitted from fossil fuel combustions. Next one is intentionally produced nanomaterials. So these are the nanomaterials which are produced by following a specific synthesis technique. These are the desired nanomaterials which are produced for a particular application. So let us now compare the nanoscience and the nanotechnology. Nanoscience consists of the identification of physical and chemical properties. Now, as you can see over here, nano silver is studied with a scanning tunneling microscope. Next is the nanotechnology, where we have to design, and next is the for a certain kind of application. Now here we have to learn how to control and mass produce the material. So the example over here is shown the antibacterial properties of nano silver. They are used in a number of products. Now, next question arises in our mind is, where does the nano lie? Nanotechnology, as a matter of fact, do not include the non-intentionally produced nanomaterials. So, this figure shows or compares the size of various objects on a nanometer scale. Some examples of nanoscaled objects encountered in daily life are as follows. Our fingernails grow 1 nanometer per second. The diameter of human hair is 80,000 nanometer. Size of a DNA molecule is 1 to 2 nanometers. A pinhead is around 1 million nanometer across. The transistor of Pentium Core Duo processor is 45 nanometers. So nanometer is, or nanoscience is interdisciplinary in that it includes the concepts of multiple disciplines such as chemistry, physics, biology, etc. It is a horizontal encompassing interdisciplinary sciences cutting across all vertical sciences and engineering disciplines as shown in this figure, which shows the impact areas of nanoscience and nanotechnologies. Nanotechnologies involves employing the nanoscience to industrial and commercial purposes. Since all industries can benefit from the nanotechnologies, thus similar to nanoscience, nanotechnologies are also horizontal, enabling convergent nanotechnologies. Nanotechnologies are horizontal as they intersect several industrial sectors and enabling because they offer the platform and the means to realize the specific devices. Additionally, since they draw together scientific disciplines which were hitherto considered separate, they are considered as convergent technologies as illustrated in the figure B. So students, let us now discuss the relevant length scale. First, for optical excitations, we should require the band gap. In the semiconductor, excitations exist just below the band gap. And the excitons, what are these? Excitons are bound hole electron pairs. So below the band gap, due to binding energy, hydrogen-like quasi-particle, hydrogen-like energy states. So we have the effective Bohr diameter, exciton Bohr diameter. Now the material dependent parameter, the same size dot of different materials may not both be quantum dots. So the Bohr diameter determines the type of confinement. So 3 to 10 times the Bohr diameter, we have the weak confinement, and delta E is approximately 1 by m star, where m star is the effective mass of exciton. So smaller than 3 Bohr diameter, we have the strong confinement, where delta E is approximately 1 by mu star, where mu star is the effective mass of hole and electron. This table describes the various exciton Bohr diameter for various semiconductors, and correspondingly we have the band gap energy. Let us now discuss about the time scale. Time scale is relevant in nanoscience and nanotechnologies, ranges from 10 to the power minus 15 seconds to several seconds. The temporal scale varies linearly with the number of particles n. The spatial scale goes as n log n. Yet the accuracy scale can go as high as n to the power 7 to n factorial with a significant prefactor. So this figure shows the typical time scales for a variety of events encountered in the study of nanoscaled objects. From this figure, it can be understood that instead of a single time scale, various different time scales exist, and all of these are significant. So any specific time scale and its importance vary from process to process. Thus, a particular time scale important for one process may not be important for any other process. Therefore, the studies involves the multi-scale problems wherein different processes are considered over different time scales. The selection of a particular time scale depends on the process under investigation. So the last question which we are going to discuss in this module is, how do we build the nanostructured objects? Now the two approaches can be followed to synthesize the nanostructured material. One is the top-down strategy, which involves taking the bulk materials and then repeatedly breaking it into smaller and smaller pieces. This can be achieved by chemical, mechanical, or any other method. The second approach is the bottom-up technique, wherein more complex assemblies are built atom by atom, molecule by molecule, or cluster by cluster. Top-down approach can produce structures with long range order and can also be used to make macroscopic connections. Bottom up approach is ideal for assembly and establishes short range orders at nanoscales. Both of these methods are possible in gas, liquid, solid states, or vacuum. The important concerns in nanofabrication are controlling the size, the shape, and clustering of the particles. So, the hybrid of both these approaches can offer appropriate means for controlled synthesis of nanoparticles, and this is the current approach followed in nanofabrication. Top down approach. In this approach, the nano sized feature or pattern is created by cutting away the material from the bulk structure, similar to a sculptor, never dealing with the atomic level of the matter. So, one of the most popular technique using this approach is lithographic pattern, where short wavelength light source is used to create the desired structure. Its main advantage is that the pattern as well as the objects are created at the desired place and no further assembling is required. So, lithography is a highly matured and advanced field owing to the developments in laser technologies as well as chip manufacturing. Visible as well as UV and X-ray sources are used in this technique to achieve the desired level of resolution. For achieving still higher resolutions and minimizing the pattern size, electron beams have also been shown to hold great promise. In these cases, the patterns are created by scanning tightly focused electron beam across the surface to be patterned. So, ion beams can also be employed for direct processing and patterning of wafers. Scanning probes can be used to create still smaller patterns by depositing or removing every thin layers. Mechanical printing methods involving nanoscale imprinting, stamping, and molding have reached 20 to 40 nanometers dimensions. The basic principle behind all these is similar. So it makes a master stamp using high resolution techniques like electron beam lithography and apply the stamp onto a substrate for creating the desired pattern. So additionally, for making thin films in the pattern of the stamp, a very thin layer of the material or the ink is deposited on the surface of the stamp. These nanoscale printing techniques offer several advantages such as facile and economic equipments. Even though top-down methods can easily create the micro-scaled patterns, achieving nanoscale resolution is the major concern for all the top-down methods. Additionally, there are planar technology and producing complex and arbitrary objects is not at all possible. So secondly, we have the bottom-up approach. In this approach, we uses assembling the object atoms by selectively placing an atom at a particular position in order to create the feature. So for assembling basic units to form larger structure, it makes use of chemical or physical forces operable at nanoscale. So as the size of the objects decreases, bottom-up approach becomes more and more significant complement to the top-down approach. So this technique reflects the natural phenomena occurring in biological systems, wherein chemical forces effectively forms all the structures required for life. Reducing clusters of specific atoms which have the capability to self-assemble to produce more complex and elaborate structures. So over the years, several techniques have been devised which follow the bottom-up approach to create the nano-structured materials. So these techniques vary from condensation of atomic vapors on the substrate to coagulation of atoms within the liquids to produce nanoparticles. Processes to fabricate the nanostructured materials from atoms involves the transformation process in solutions. For example, sol-gel technique, plasma synthesis, spraying, chemical and physical vapor depositions, etc. Availability of starting materials, often termed as the precursor, is a critical aspect in nanoparticle synthesis processes. So students, let us now summarize what we have learnt in this module. First, we discussed about the nanoscience and nanotechnology. Secondly, we discussed the various types of nanomaterials. Thirdly, the length and the time scales were also discussed. Lastly, we discussed now how do we build the nanostructured objects. So we uses two approaches, top-down approach and bottom-up approach. Thank you.